Hi everyone. So in this video we discuss the downsampled, what's known as downsampled convolution or convolution with a stride. And the motivation for it is very obvious. So basically when we discussed pooling with a stride, we said that one of the major advantages of pooling with a stride that's bigger than one, is that basically you reduce the number of units that's going on to the next layer. Right? But pooling doesn't only do this reduction of number of units to the next layer. There is also a pooling function in the computation of each of the pooling units, right? So if the only motivation for doing pooling with a stride is just reducing the number of units going to the next layer, then you would be better off doing convolution with a stride. And convolution with a stride basically means that you don't do convolution, you don't apply the convolution kernel with a shift of 1, but you increase the size of the shift. So for example, if we have here, this is the input to the convolutional layer, right? So this is the input. And each of these is the output of a convolutional kernel, right? So this is the output of conv kernel, right? So this is a kernel of width 3 in that example, and this is a stride of 2, right? So instead of the stride of 1 would correspond to a shift of 1. So basically here the maximum limit, so remember in pooling the stride was limited by the pooling width. Here, the stride is limited by the size of the convolutional kernel, right? So the stride should not, in any dimension, should not exceed the size of the convolutional kernel. Otherwise, we are missing parts of the input. Now, what's the advantage here over just doing pooling with a stride is that you do less computation, right? So you reduced, when you do convolution with a stride stride equal 2 or downsampled convolution with a stride 2, you reduce the number of computations, right, by half. You reduce the number of computations, convolution operations that you do by half. So it's not only that you reduce the number of units going to the next layer, which also happens here, but you also reduce the number of computations in the convolutional kernel step, right? But you might opt for pooling with a stride if the pooling function is useful, right? So that becomes a bit tricky, and you could also have a combination of convolution with a stride and then further reduction in the dimensions through pooling with a stride. In practice, one of these is typically needed, at least for one of the layer in a deep, like for few of the layers in a deep architecture. And the reason is that usually you handle data, input data with very high dimensions. Like we mentioned in the last example, for example, the images usually come with channels corresponding to colors, right? So imagine I'm processing these images. So each kernel, now each convolution operation happens in 3 dimensions, right? The 2 dimensions corresponding to the image itself and the 3rd dimension corresponding to the color. Also, another factor, if I'm operating in batch mode, so I am computing both the forward and backward propagation across all the examples in a mini batch. So I stack the hidden unit activations corresponding to all the examples in the mini batch at once. So I do the computation of the convolutional kernel for all the examples in the mini batch at once. So that will be a 4th dimension, right? So you will end up with a 4D tensor, right? So these computations are expensive, what makes it worthy to reduce these computations, right? So so that's basically the takeaway lesson from this video is if your goal of designing pooling with a stride, if the only goal was not the pooling function, it was just introducing the stride, then you are better off doing convolution with a stride instead, because there you would also reduce the computations. Sounds good? Thank you.